Good day, everyone. I am Carl P. Pasco, the third reporter of our topic. Our topic is all about evaporation, transpiration, interception, depression, storage, and my topic is about interception. First, we all know what is interception. Interception is the process by which water is captured on vegetation, leaves, bark, grasses, crops, etc. During a precipitation event, intercepted precipitation is not available for runoff or infiltration, but instead is returned of the atmosphere through evaporation. Interception can be high as 2 mm during a single rainfall event, but typically removes about 0.5 mm during a single rainfall storm event. The quantity of water removed through interception is usually not significant for an isolated storm, but when added over a period of time, it can be significant. There are three main components of interception. First, interception loss. The water that is retained by vegetation surface is later evaporated into the atmosphere or absorbed by the plant. Interception loss prevents water from touching the ground surface and is regarded as a primary water loss. Second is through fall. The water which falls through spaces in the vegetation canopy or which drips from the leaves, twigs, and stems and falls to the ground. A third one is stem flow. The water which trickles along the stems and branches and down the main stem or trunk to the ground surface. Factors affecting interception. Interception storage, the ability of vegetation surfaces to collect and retain precipitation. Evaporation. Even when the interception storage capacity is exceeded, water may be lost by evaporation of leaf surfaces. Duration of rainfall influences interception by determining the balance between reduced storage of water on vegetation surfaces and increased evaporated loss over time. Rainfall frequency. The highest levels of interception loss occur when the leaves are dry and interception storage is large, so the frequency or rewetting is more significant than duration and amount of rainfall. Precipitation type. The contrast between rain and snow. Snow clings to leaves and branches more. Interception loss is limited due to low temperature and evaporation rates. Type and morphology of the vegetation cover. Interception losses are generally greater from trees than other types of vegetation. Okay, there are formula for computing on this interception. Interception losses usually occur during the first part of a precipitation event, and the interception loss rate trends towards zero rather quickly. If the total rainfall volume is less than S, then all rainfall will be intercepted. Potential interception losses during storm can be estimated. So the formula is Li is equal to S plus KET, where Li stands for the volume of water intercepted, and the unit is mm. The K, the ratio of surface area of intercepting leads to the horizontal projection of the total area. E stands for the evaporated rate, mm per hour, millimeter per hour, during the storm period, and T stands for duration of storm. The unit is hour. So I have something to para mas masabtan siya. Ako ipakita nga video, nga example from YouTube.
This is about interception. Interception is a very important part of the surface water cycle. Super. So the reason why I'm making this presentation is because in the timed pressured situation of the exam, candidates sometimes confuse interception with infiltration. So when you've watched this, you won't ever do that again. These are the 3 questions that I'm going to take you through. Interception is defined as the storage of water in or on vegetation before it reaches the ground surface. So here we have a leaf, it's rained on the leaf, and water droplets have formed on the surface of the leaf, and they're being held there by the leaf. The amount of interception will depend on the shape of the leaf. It will depend on the form of the leaf. You can see here this leaf has got specific runnels in it where the water could be stored, whereas this one from an older tree is relatively flat. All kinds of vegetation will intercept some water, but trees are the most effective interceptors, and this depends on their density. So if we look at this coniferous tree, like a Christmas tree, one which is evergreen all year round, it is able to intercept around 25% to 35% of all rain in a year. By contrast, deciduous trees like this one, which lose their leaves in autumn, here you can see the leaves have gone red, they're going to fall off, they will only intercept between 15 and 25% of annual precipitation. And so the type of the tree, the density of the canopy, and obviously the density of the trees in a plantation, in a forest, is going to affect how much water is intercepted by that tree. The duration and the type of precipitation that fall also have an impact. So let's imagine it starts to rain in this forest. The leaves start to collect water. As the rain proceeds, more water is added to the leaf. At a certain point, that leaf becomes too heavy, and all of a sudden the leaf will suddenly droop, and then we get leaf drip. The process of leaf drip will empty the interception store. So if it's only a light rain shower, interception can be close to 60 or 70% of that rain shower. But if the precipitation intensity and duration is long and intense, then we will get less interception because it will then follow the pathway of leaf drip or even stem flow and will reach the ground surface. Secondly, in boreal forests, like those in Siberia in the northern hemisphere, a substantial amount of precipitation falls as snow. During the winter, the snowfall accumulates on the branches of the tree, and the trees are structured in such a way that they actually catch a huge amount of that snow. It's estimated that between 10 and 20 kilograms of snow can be stored in the branches of these trees per metre squared of forest. So this is very important, and it means that the precipitation is stored, and then in spring it's suddenly released in the spring snow melt, which has an impact on the river levels and on the rest of the catchment's hydrology where the trees are. Interception loss is the process by which a droplet of water which has landed on the leaf then goes back into the atmosphere again via the process of evaporation. This is controlled by temperature. Higher temperatures, more evaporation. It's also controlled by wind speed, higher wind speed, more evaporation, more loss of water from the interception store. And thirdly, it's controlled by humidity, because in conditions of high humidity, the evaporation rate is lower. Human activity affects interception in a number of ways, and you can probably think of lots of these, but here's 2. Number 1 is deforestation. If the forest cover is lost, obviously there's going to be no foliage to catch in the incoming precipitation. Therefore, we see more surface runoff. More surface runoff leads to increased water in the river channel, leads to increased risk of flooding, like we've seen in the tropical forests and the Madeira Basin in the Amazon. Secondly, many areas of forest have been turned over for agriculture. For example, here we have one of the world's most used products in food, the soya bean. When the soya bean is planted, obviously it's able to intercept incoming precipitation. But when it's harvested, then there's no interception whatsoever. So when cereal crops of all kinds are harvested, this means that the sunlight then reaches the ground surface, and that can lead to baking effects, then reducing infiltration, which we'll look at in a later presentation. One of the fruits which is really, really well liked in my household is the mango. Here's a picture of a mango tree, here's a picture of an unripe fruit, and here's a picture of a mango which is ready to eat. Let's look at the data on the mango tree. These two graphs are taken from some really recent research done in 2018 on the mango tree. So the mango tree was involved in two precipitation events, event 1 and event 2. Study these graphs, and then I'd like you to suggest reasons why the blue line, the interception, in this tree were different for the two different events, rainfall events. Rainfall is shown in red. Press pause now, have a think about this before you move on. So a couple of things to notice here. On the y-axis we've got two different scales. In event 1, around 13 millimetres of rainfall. In event 2, however, around 79 millimetres of rainfall. And we can see that event 2, there's a much bigger gap between the amount of rain that falls and the amount of rain that can be intercepted. So we're going to assume that where this occurs, where this level flattens out here for the interception, we were assuming there that probably that's because the interception stores on the mango tree, every leaf is full. So at this point, after this point, we're expecting that leaf drip processes and stem flow processes will be more important. You will have noticed that the red line showing the rainfall shows a different pathway. Here the onset of rain is low and the amount of rain is also low. And so most of the graph of interception tracks alongside the rainfall, and the mango tree is able to absorb almost all of the rainfall storm in this case. However, when the rain is more intense, the tree, there's a bigger gap here between interception and precipitation, and the reason for that is because a lot of the rain is running off the tree, it's running down the stem, and it's been involved in leaf drip processes. In summary, interception is affected by wind, humidity and precipitation. Coniferous trees like this one, evergreen trees, are better at intercepting rainfall than deciduous trees. Complex stratified forests like the tropical rainforests are much better at intercepting rain than soya plantations or palm oil plantations. And human activity reduces interception. Urbanization, farming and deforestation will all have this effect.
Hello everyone, my name is John Lloyd Mariano, and today we will discuss about interception and depression storage, which is under Chapter 3, Obstruction from Precipitation. First is interception. Interception is the removal of water that wets and adheres to plant foliage, buildings, and other objects above ground surface. This water is subsequently removed from the surface through evaporation. Interception can be as high as 2 millimeters during a single rainfall event, but typically removes about 0.5 millimeters during a single rainfall or storm event. The quantity of water removed through interception is usually not significant for an isolated storm, but when added over a period of time, it can be significant. It is thought that as much as 25% of the total annual precipitation for certain heavily forested areas of the Pacific Northwest of the United States is lost through interception during the course of a year. Interception is the process by which water is captured on vegetation such as leaves, bark, grasses, crops, etc. during a precipitation event. Intercepted precipitation is not available for runoff or infiltration, but instead is returned to the atmosphere through evaporation. Interception losses generally occur during the first part of a precipitation event, and the interception loss rate trends toward zero rather quickly. There are three main components of interception. First is interception loss. The water that is retained by vegetation surface that is later evaporated into the atmosphere or absorbed by the plant. Interception loss prevents water from reaching the ground surface and is regarded as a primary water loss. Next is throughfall, wherein the water which falls through spaces in the vegetation canopy or which drips from the leaves, twigs, and stems and falls to the ground. Last is stem flow. The water which trickles along the stem and branches and down to the main stem or trunk to the ground surface. Interception loss is described by the equation L sub I is equal to S plus KET, wherein L sub I is the total volume of water intercepted, S is interception storage, K is the ratio of the surface area, the leaves, to the area of the entire canopy. E is the rate of evaporation during the precipitation event, and T is for time. The total interception is dependent on the storm duration, as longer duration storms allow more evaporation from the canopy during the storm event. The intensity of the storm also plays a role in canopy interception. However, there is debate as to whether intensity increases or decreases interception storage in canopy. There are factors that affect interception. First is interception storage. The ability of vegetation surfaces to collect and retain precipitation capacity will be the highest at the onset of rainfall when the vegetation is dry, when water is held by surface tension. Next is evaporation. Even when the interception storage capacity is exceeded, water may be lost by evaporation of leaf surfaces, which increases in windy conditions, though the interception storage capacity may be reduced with increased wind speed. Duration of rainfall influences interception by determining the balance between reduced storage of water on vegetation surfaces and increased evaporative loss over time. Total interception losses increase with duration of rainfall, but only gradually, though the relative importance of interception decreases with time. The importance of interception decreases with time due to duration of rainfall and changes in interception storage capacity. Last is rainfall frequency. The highest levels of interception loss occur when the leaves are dry and interception storage is large, so the frequency of rewetting is more significant than the duration and amount of rainfall. Our next topic will be depression storage. Depression storage is the term applied to water that is lost because it becomes trapped in the numerous small depressions that are characteristic of any natural surface. When water temporarily accumulates in a low point with no possibility for escape as runoff, the accumulation is referred to as depression storage. Depression storage refers to small low points in undulating terrain that can store precipitation that otherwise would become runoff. The precipitation stored in this depression is then either removed through infiltration into the grounds or by evaporation. Depression storage exists on both pervious and impervious surfaces. Impervious surfaces are generally human-made, like buildings, roads, parking lots, bricks, or asphalt, while pervious surfaces include vegetation, water bodies, and bare soil. According to Linsley, the volume of water in depression storage at any time during a precipitation event can be approximated as V is equal to S sub D times the quantity 1 minus E raised to negative K V sub D, where V is the volume of water in depression storage, S sub D is the maximum storage capacity of the depression, V sub D is the rainfall excess, and K is the constant equal to 1 over S sub D. There are 6 factors that affects depression storage. First is nature of terrain, next slope, third is type of soil surface, fourth is land use, fifth is antecedent rainfall, and last is time. There are empirical estimates of depression storage for storms. For sand, we have 0.20 inches, for loam, 0.15 inches, for clay, 0.10 inches, for impervious areas, 0.62 inches, and lastly, for pervious urban, 0.25 inches.